Hello pre-calculus students, and welcome to a video on the greatest integer function. So this is lesson 5.3, so this is Friday of the 5th week, and this is the in-class lesson. Alright, so this is another parent function, so we're going to be adding, if you look at the page of notes here on the bottom, we're going to be adding another page or another half page or function to our list of parent functions. Okay, so it can be a pretty important function in some applications. So define the greatest integer function, graph with some vertical transformations. So we're only going to look at transformations that are vertical for this class on the greatest integer function. But first let's see what it is, okay? So this is a type of step function. You'll see why once we get the graph. It looks like a staircase. And this one type of step function is the greatest integer function. There are other step functions. Okay, so what is the greatest integer function? So first of all, the notation that your book uses is int, stands for greatest integer function. So int of x, or greatest integer of x, it means the greatest integer less than or equal to x. The greatest integer less than or equal to x. Okay, so the greatest integer less than or equal to x, and I put here it's like rounding, kind of, but it's always rounding down. So even if you have something like 2.8, you round down because the greatest integer less than or equal to 2.8 is 2. So it's always rounding down. Sometimes that's called truncating. You just get rid of the decimals and you just keep the trunk of the number, which is the integer part of the number. So let's look at some numbers here and find the greatest integer of 0.5. So the greatest integer less than or equal to 0.5. Remember, integers are positive and negative whole numbers and 0. So the greatest integer that's less than or equal to 0.5 would be 0. And the same is true even if you get all the way up to 0.99, even though that rounds up to 1, it rounds to the greatest integer, you would just call that 0 also. Okay? Less than or equal to 0 is also 0. Alright, so you'll see how this looks on a graph in a minute. Less than or equal to negative 1 is negative 1. Less than or equal to negative 0.5, let's just look at this one because it can be a little bit tricky. So here's negative 1, here's 0, and negative 0.5 is somewhere in the middle, right? There's negative 0.5. So the greatest integer less than or equal to that is negative 1. Less than or equal to negative 0.99 would be like here, and that's also negative 1. Less than or equal to square root of 2, which is around 1.4, 1.3, something like that, would be 1. And the greatest integer less than or equal to pi would be 3. Okay, that's just kind of to give you an idea of what this looks like. All right, let's make a little t-chart with x and the greatest integer of x. This is just a sideways t-chart, and I'll put in the x values, and then I'm going to give you a minute to put in some y values. So 0.5, 0.9, yes, some of these might duplicate what we have up above. 1, 1.5, 1.9, 2, negative 1. We'll go with negative 0.5, negative 0.9. And last one, make it negative 1.5. We're just going to try to get an idea of what a graph looks like. So take a minute, see if you can write down all of the greatest integers for these. Okay, they're there. Now let's just plot these points on the graph. Alright, so we've got just a normal graph here. We've got 0, 0. I'm going to plot that point. We've got 0.50, so maybe right in the middle, right about there. We've got 0.90, so when it gets really close to 1, it's still 0. But when we get to 1, it takes a jump, right? It doesn't have a point here. So we want to indicate where this sequence of points right here ends, and there's a hole there at 0, because at that point, at x equals 1 right here, it jumps up to 1. So there's a point up here, but a hole down here, and this is what we would call the first step. Okay, right there's the first step. Then if we continue on, we've got 1.5 has an output of 1, and 1.9 does 2, but when it goes to 2, it jumps again. It jumps up to 2. So here at 2, 1, there's a hole, and there's the second step, and the point at 2 jumps up to 2, so it's like that. And this is going to continue to make steps, and each step has a hole on the right and a point on the left. So this step has a hole on the right and a point on the left. Then it's going to jump up from here at 3. It's going to jump up to 3, so there's a point up there. It goes all the way to 4 where there's a hole. And then at 4 it jumps up again, and so on forever. So there's the 4th step. So this would be, for example, the point 1, 1, while this is the hole at 1, 0. And I'll fill in the rest of the points. Let me put in some in a minute. But let me put in some negative points here. The pattern will continue. So for example, if you plug in -1, the output is -1. So if we plug in -1, the output is -1. That's a point on the left. But if you plug in I could have put -0.1 here. It doesn't matter. Anything between here and here is going to still be -1 until you get to 0. And then we already have over here 0. It has an output of 0. So at 0, the output is 0, not here. And all of these would be points. So the steps, there's no surprises there. The pattern just continues. So I'm going to finish the pattern and put a bunch of ordered pairs in here, and then you try to do the same thing. Okay, and there you're looking at your parent step function, several steps, and you can see where the points and holes are. Notice that there's always a hole on the right, there's always a point on the left. And as long as there's no change in the x's, that's going to remain the same. Okay, so and that's what we're going to focus on today, because we're only focusing on vertical transformation, so nothing horizontal, nothing that impacts the inputs, just impact the output. So we're always going to have the holes will always be on the left. The holes will be on the right and the points will be on the left. All right, so let's look at this as a parent function now, and I'm going to just name it, and we'll plot it, and then we'll just name a bunch of properties of it. So this is f of x or y equals the greatest integer of x. Okay, that's the new parent function, and there's really no commonly accepted points for these. We just can pick 4 or 5 from up here, so we can just pick 0, 0. We could pick 0.50, enough to at least get one good step, and then we'll pick 1, 1, and then we'll pick 1.51, and then we'll pick 2, 2. Like I said, there's really no commonly accepted points there. So I'm going to plot it, and then we'll look at it. You can look at it from up here, see if you can go through these, and then we'll talk about them when we have them all filled out. Okay, so there you see the properties, and they're kind of weird for greatest integer functions compared to most functions. It's kind of hard to describe some of these. Like, for example, is it increasing? Well, it is going up, but they're really constant intervals. Every interval is constant. So there's not really an interval where the function is decreasing, or increasing or decreasing, but it's definitely not decreasing anywhere. There's definitely no local max or min. It is definitely not continuous. You have to lift your pencil every time you jump from step to step. End behavior does look something like a cubic function or an identity function. As you go towards positive infinity, as x goes this way, f of x is getting higher. Okay, so it is following that pattern. As x goes towards negative infinity or going to the left, the function is getting lower. So that is true. Okay, when graphing greatest integer function, this is really supposed to be the first sentence of the next page. So when we're graphing, let's take a look at this, and we're going to look at a couple of graphs. So let's look at a couple of, first we're going to simplify it, and let's just see how we're going to simplify this. First, when we graph, we always want to consider at least three positive and 3 negative steps. It's often easier to first consider the corresponding linear function, and that's definitely going to apply to what we do today. And we're going to focus on just vertical transformation. So notice the input. There's nothing changing on the x in either one of these, and so that's going to be what we focus on. So when that's the case, if nothing changes, then that means that these steps are not going to move, they're not going to stretch, and they're not going to reflect. So in other words, there's always going to be a step here of this length. It's not going to stretch, it's going to start here and it's going to go this way. It's not going to reflect to the other side. So the point will be on the left, the hole will be on the right, and it will continue to be 1 unit long. What we're going to look at is vertically stretching, vertically moving these up or down, and that's it, okay? And vertically reflecting potentially. All right, so let's just take a look at how we can do that. So when I said consider the linear function, let's do that. Let's graph the linear function first. So if we have this greatest integer function, let's start by graphing the linear function. And let's just make a normal graph of y equals 1/2 x minus 1. So it has a y-intercept here. It goes up. It's got a slope of 1, so it goes up 1 and over 1/2. I mean, so it goes up 1 and over 2. So something like that. And then up 1 and over 2. And so let's graph that line. Let's connect it lightly. This is not the graph, but this is at least enough to get us started. And we don't really need the whole line, but I'm just going to put it anyway. All we need is those points. So there's another one here, and another one here, and another one here. Now the beauty of this, things that make this fairly easy, is that these are points that are part of the greatest integer. These are the left sides of our steps. And so all we really have, and the steps will not change their length. They're still going to be 1 unit long. So if this is, I made this 2, right? So if this is 1, the step is going to have a hole right there, and a hole right there, a hole right there, and a hole right there. Let's see. A hole right there, a hole right there. We're not quite done because we can't leave it like that because there's too many gaps in it. So we just have to fill in the other points. So this was the easy points to graph because they were the ones that we used to make our line. But remember that the domain is all real numbers, so we can't have these gaps that we have. So I'm just going to fill in the gaps. So there's got to be there's got to be one in between here, so it's going to have a hole right here and a point right here. I'm just going to do this in the pen. So a hole here, a point here, and I should have probably stretched it, but it's too late now. So these steps are really small. So there's always a hole on the right, point on the left. There are all these points on the left, by the way. They are on the graph. They're just kind of hard to see because the graph is pretty small. But there it is. Okay, we can put a couple ordered pairs on here. We have well over the required 3 steps in each direction. I'm just going to put a couple of ordered pairs on here to make sure that's clear too. Okay, there's a couple points. And by the way, this is moved down, as you can see by the first step being moved down. And it is vertically compressed. As you can see, these steps are compressed. They're closer together. All right, let's look at one that's vertically stretched. And let's just plot the line first. So the line has a y-intercept of 1. So we'll plot that line at a y-intercept of 1, and now a slope that goes down 2 and over 1. So it's something like that, down 2 and over 1. And we'll connect a bunch of these points. And this will be easier to graph because this one is stretched rather than compressed. And the thing that made the other one a little bit hard to see was that it was compressed. So we've got this graph. We've got another point here, continues here. And now when we make our steps 1 unit long, they're going to fill the entire domain. It's going to be a little bit easier. So let's see. So we've got this one which starts out at 0. So remember, the whole thing moves up 1. So there it is, moved up 1. There's a point there and a hole on the right. Always a point on the left, hole on the right. Here there's a point on the left, hole on the right, and there it is. Point on the left, hole on the right, point on the left, hole on the right, and you get the idea. And we can put a couple of these ordered pairs in. Okay, there's enough. There's a couple points. And we should really we should follow the rule and plot at least 3 steps in the positive direction. I'm not going to put ordered pairs for all of them, but notice I am writing ordered pairs for the holes, and you should do that. You should write at least a couple of them just to make sure that holes are still important, and we label them even though they're not part of the domain. They're not points on the graph, but they're still important for understanding what the graph looks like. Okay, I hope you found this video helpful.